Hello everyone, in this video we're going to be looking at section 11.4, which is the cross product of two vectors in space. Alright, so subsection 1 is just introducing the cross product. Many applications in physics, engineering, and geometry involve finding a vector in space that is orthogonal to two given vectors. In this section we will study a product that will yield such a vector. Okay, so the definition of a cross product of two vectors in space. Let U be this ijk and V be this ijk, be vectors in space. Then the cross product of U and V is this big, long, awkward formula. If you're able to remember that, then I will be very impressed. I am not. So, the convenient way to calculate the cross product is to use the determinant form with cofactor expansion. So in other words, what we do here in order to find the cross product is we say, okay, let's find the determinant of this matrix that has ijk in the first row, and then in the second row it has the ijk components of U, and in the third row it has the ijk components of V. Right? And then what we do is we find the determinant of that matrix. If you're unfamiliar with it, we'll go through it right here. So in order to find the determinant of this 3x3 matrix, we say, okay, let's put the I. Let's look at the I spot right there. So that's why I put that I there. And then let's pretend that this column and this row don't exist. So I say, okay, because I went on this corner here with the I, then I write the corresponding that's left over, right? The corresponding 2x2 matrix that's left over. And then when I go to the next spot, which is J, because J is in the second spot, it gets this pesky negative sign. So that's one thing you really have to remember, is that it gets a negative sign because it's in the second spot. So then because I'm in the J spot, now I pretend that the J row and the J column don't exist, and then I have the 2x2 matrix that I circled there left. And then finally we get to the third column in the third spot here, which is this K. So I put the K here and I pretend that the K column and the K row don't exist, and this is my corresponding 2x2 left. Now what I do, these are all 2x2 matrices. In order to find the determinant of a 2x2 matrix, you multiply the top left with the bottom right, and then subtract the top right and the bottom left, right? So in other words, it's like diagonals like that. So I go, if I were going to do this, or I go like boom, boom, which would be these two guys, and then minus boom, boom, which would be those two guys. And I do that for each one of those 2x2 matrices here, making careful that I have this negative sign here because of that negative sign with the J. So that is how we find the cross product of two vectors. One thing to note is the cross product of two vectors is a vector, right? In the last section we looked at the dot product. The dot product of two vectors is a scalar, right? It's a number. Here the cross product is going to have a component. This will be the component for I, this will be the component for J, and this will be the component for K. So it's a vector. And again, this vector is a vector that is orthogonal to the two vectors. So in the case where I have a vector U and V, and I find the cross product U dot V is the vector that is orthogonal to both U and V. Right? Okay. So now let's go ahead and find the dot product of, the cross product of some vectors here, practicing using this whole idea of the determinant of the matrix. Okay, so I want to find U cross V. So what I do here is I say this is I, this is J, and this is K. And then now I put, since it's U is first, U goes in the second row. So and it's just the coefficients. So here I would have 1, -2, 1. And then the coefficients or the components of V, which would be 3, 1, +2. And I'm going to find the determinant of this matrix. Right? So I'm going to, right now, I'm going to expand around I, so I'm going to pretend that this row and this column don't exist. So I say, okay, -2, 1, 1, 2, and then I have the I, because we expanded about the I column and row. And now I need a subtraction sign because I'm going about the J next. So I do the j, I pretend this row and this column don't exist. So now I have 1, 1, 3, 2 times j, and then plus, because we'll have a plus with the k, and now we pretend that the k row and column don't exist, and I get 1, negative 2, 3, 1 times k. Okay, so now what I do is, this is the determinant of a 2 by 2 matrix. So again, this is our formula here. In other words, I multiply negative 2 times 2, so that gives me negative 4, minus 1 times 1. Right, so negative 2 times 2 minus 1 times 1, which is 1, and then I multiply that times I. Minus, and now I do 1 times 2, which is 2, and then I do 3 times 1, so minus 3 times 1, which is minus 3, j, and then plus 1 times 1 is 1, minus, and then when I multiply this, it's negative 6, so in other words, plus 6 here, k. So now I just simplify, and I get negative 5 I hat minus, and that's minus negative 1, so this would just be plus j, and then plus 7 k. So that is my cross product vector. That is my u cross v. And again, notice that it is a vector, and this is the vector that is orthogonal to both u and v. Okay, so now let's look at v cross u. So in other words, switch my rows here. So I still have the I, the j, and the k, but now I put the components of v first. So I put 3, 1, 2, and then I put 1, negative 2, 1. And then this time we'll go a little bit faster. So if I pretend the I doesn't exist, I'm left with 1, 2, negative 2, 1 times I, minus, now pretend the j row and column don't exist, so I'm left with 3, 2, 1, 1 times j, plus, now pretend k doesn't exist, so 3, 1, 1, negative 2, k hat. So now I have 1 times 1, which is 1, minus negative 2 times 2, so that's going to be plus 4. And then minus, and then I have 3 times 1, so 3 minus 2, j, plus 3 times negative 2, which is going to give me negative 6, and then minus 1, which is going to, and then k. And so here I get 5i minus j minus 7k. And what do you notice about u cross v and v cross u? If you notice, they're exactly the same, except one is the opposite. So in other words, all the opposite signs. So in other words, v cross u is the same as minus u cross v. And that's actually this property 1 in the next theorem. So in other words, the cross product is not commutative, right? Because if I switch the order, the signs are going to change. So it's not exactly the same. So they're not commutative. So now let's look at when we take v cross v. My first row is I, j, k. And then now v is going to be 3, 1, 2. So 3, 1, 2. And then it's v again because we're doing v cross itself. So 3, 1, 2. So pretend I row and column aren't there. I get 1, 2, 1, 2, I minus 3, 2, 3, 2, j plus 3, 1, 3, 1, k. And in this case, I would get 2 minus 2, I minus 6 minus 6, j plus 3 minus 3, k, which is just going to be 0 I minus or plus 0 j plus 0 k, which is just the 0 vector. All right? and that's actually proving another part of the theorem, or not proving one of the theorem, but illustrating the theorem. Here, this guy, any vector cross product with itself is equal to 0, right? So we illustrated that there. Okay, so some interesting properties about the cross product. Let u and v be non-zero vectors in space, just like this vector, say this is our v and this is our u. And theta is the angle between them, just like the theta is there. If we have this situation, then u cross v is orthogonal to both u and v. We knew that because that was kind of what we had talked about at the very beginning for what the definition of the cross product is. But this theorem is basically, if you look at the book, they prove that u cross v is actually orthogonal to both u and v. The magnitude of u cross v is equal to the magnitude of u times the magnitude of v times sine theta. U cross v is equal to the 0 vector if and only if u and v are scalar multiples of each other, which means if and only if they are parallel, right? Because remember, if u and v are scalar multiples of each other, then they are parallel, right? And this property too comes from this, looking at this parallelogram, and that's also what property 4 tells us. It says that the magnitude of u cross v is the area of the parallelogram having u and v as adjacent sides. So in other words, this pink parallelogram, if I were to find the area of that, it's equal to the magnitude of u cross v. And that makes sense because in order to find the area of a parallelogram, it would be the length of this side, which is the magnitude of u, times the height, which is the magnitude of v, times sine of theta, because that's what the height is. And then if you look at property 2 there, that is exactly equal to the magnitude of the cross product. Okay. So one other thing to talk about here is both u cross v and v cross u are perpendicular to the plane determined by u and v, right? So u and v are 2 vectors, so they make a plane. And to remember the orientations of u, v, and u cross v, we compare them to the unit vectors I, j, and k, which is I cross j. So in other words here, remember I is going to be the positive x-axis, right? And this is the positive y-axis. And so I cross j, which is the k vector, goes upward, right? And that is how we keep track. And then if I did j cross I, well, that would be negative k, because remember, if you change the order, then you give it a negative sign. So in other words, if I went the other way, then I would get this guy right here. This is negative k, which is j cross I. So that's how you know whether your cross product vector points up or down, because we know that it's perpendicular, so it needs to point either up or down. And the way we know is by what's called the right hand rule. Because when I said I was the first vector and then multiplied it or cross product it with j, that's like moving to the right, and so that means that my cross product is going to point upward. So in other words, if I take u cross with v, and if I move, however I move from the right to u to v, then my cross product is going to stick up from that. If I had v cross u, then I would be moving to the left, and that's how I know v cross u is going to point downward. Right, so let me clean this up a little bit. Oops, I want to keep that. So we can keep that. We can keep that, and then this guy down here, again, this is v cross u, right? Because it's the opposite of u cross v. Right, so anytime I go anytime I have 2 vectors, I go from the first component to the second component of the cross product, then I know that my perpendicular vector or my orthogonal vector u cross v is going to point upwards. And if I went the left, then I know that my perpendicular vector, my orthogonal vector points downwards. Okay, so let's find a unit vector that is orthogonal to both u and v. So in order to find a vector that's orthogonal to both u and v, that vector is u cross v. So recall that the vector u cross v is orthogonal to u and v. All right, so our game plan here is to find u cross v because that is a vector that is orthogonal to both u and v. And then because it says find a unit of vector, we can normalize that. In other words, divide it by the magnitude of u cross v, and that will give us a unit vector that's orthogonal. Right? So first we need to find u cross v. In order to do that, we take I, j, and k. U cross v, so this is 1, -4, 1, and then 2, 3, and then the k for the k component for v is 0. So this ends up being -4, 1, 3, 0 times I minus 1, 1, 2, 0 times j plus 1, -4, 2, 3 times k. Scoot it over a little bit. So now I would get 0 minus 3i minus 0 minus 2j plus 3 minus negative or plus 8k. So I end up getting here -3i plus 2j plus 11k. So that is a vector that is orthogonal to both u and v, but it's not a unit vector. So to make u cross v, right, because this is equal to u cross v is what we just found, right? So to make u cross v a unit vector, we must normalize it. And that's kind of a fancy word, but remember, normalize it is that idea that I'm going to take, in other words, we're going to find 1 over the magnitude of u cross v times the vector u cross, that looks like a v, u cross v. And that, this scalar here times our vector is going to give us a vector that has length 1, which means that it's a vector, it's a unit vector. All right, so first obviously we need to find the magnitude of u cross v. So the magnitude of u cross v, remember, in order to find the magnitude of a vector, we just square all of its components and add them up and take the square root. So I get -3 squared plus 2 squared plus 11 squared, all underneath the square root. And if I plug that in my calculator, I would get the square root of 134. Right? So what did we want to find? The unit vector that's orthogonal. We want to take 1 over the magnitude of u cross v times the vector u cross v. So in other words, we want to take 1 over the square root of 134 times our u cross v vector, which we found to be -3i plus 2j plus 11k. And so remember, we just multiply our scalar through. So I get -3 over 134 underneath the square root times I plus 2 over top of the square root of 134j plus 11 over the square root of 134k. And again, like most of our unit vectors, it's pretty ugly, but it does have a length 1, and because it was the cross product normalized, it is orthogonal to both u and v. All right, we'll go ahead and end this video here and pick up with the rest of section 11.4 in the next video.